Hello, welcome back. Today we're going to talk about decibels. Now it's important to know what decibels are and what they are not. A decibel in and of itself is not an absolute measurement, like an inch or any other unit of measurement, any kind of value. So anything just that's a standalone dB, if you say, oh, this is 5 dB, that really has no meaning because you have to reference it against something. It's kind of like saying a percentage. You'd say, oh, this is 50%. Well, 50% of what? Is it 50% greater, less than? But a dB by itself is simply a ratio. It's a comparison of two values. It's logarithmic, which is very helpful in our work because, similar to octaves and hertz and whatnot, decibels is a great way to translate our hearing perception in terms of how loud something is and how soft something is, because we hear in a very non-linear manner. Decibels are very helpful to us in that regard. Now, when you're dealing with decibels, you have to be careful of whether you're dealing with power or watts or pressure or voltage. So if you're talking about sound pressure level or SPL or certain voltages in within your console, most of the time we're probably going to be dealing with the 20 log calculation here, because most of the time we're going to be dealing with pressures or voltages. Although there are times, of course, when we're dealing with power amplifiers, if we're comparing watts, that we use a 10 log formula, which you can see there. And the structure of the formula is that you either have the 10 or 20 multiplier, and then take the log of the measurement value, the value you're looking to compare. That is, let's say, for example, you want to test, you have 1 voltage, and you want to turn the voltage into a decibel value. Well, you take that measured value voltage and divide it by the reference value. Well, what are those references? I'm glad you asked. The reference values depend on what kind of decibel you want to turn it into. Because remember, we talked about a dB by itself is not an absolute measurement of anything, but a dBu, dBV, dBm, dBSPL, those are actual values because they are a comparison to a known reference. And in this case, the reference for dBu is 0.775 volts. The reference value for dBV, which we may also call dB big V, is 1 volt. Now the reason we call it dB big V, or you'll hear me refer to it as dB big V, because in some older texts you'll see dB lowercase v, which is the exact same thing as dBu, which they changed to dBu because of clarifications and to help keep people from confusing the two. So anyway, the reference value for dB big V is 1 volt. dBu is 0.775 volts. And you'll also see dBm, although it's not really used a whole lot anymore, though you may see it sprinkled around here or there. It's really not a good reference because it's a value of 1 milliwatt is the reference value, but it's only into a 600 ohm load. Now, back in the olden days, when everything was 600 ohms to 600 ohms as the input or output impedance, that would be perfectly fine because we'd be dealing with those impedances all the time. But now we don't really deal with fixed 600 ohm impedances. We deal with bridging impedances, that is, low output impedances and high input impedances. So we deal mostly with dBu. But if you do run into dBm, you can kind of cheat and call the dBm you can kind of convert that to a dBu. It's not really correct, but for most of the times it kind of works, simply because of when you take that dB 1 milliwatt into a 600 ohm load, the voltage you get is 0.775 volts, which is the reference value for dBu. So you may see dBm, but generally we much rather work with dBu. Now dBSPL, of course, you all know and love, our sound pressure level. And the reference value is the threshold of human hearing, which is 0.0002 dynes per centimeter squared. So again, these 4 reference values, dBu, 0.775 volts, dB big V, 1 volt, dBm, 1 milliwatt, and dBSPL is 0.0002 dynes per centimeter squared. And if you need to go back from dBV or dBu to volts, you follow this slightly convoluted formula. Now, as an example here, let's say we wanted to convert plus 4 dBu back to an actual voltage. Well, we follow the formula here of 0.775 times 10 to the power of dBu that we want to convert, divided by 20. So we just plug in plus 4 dBu into here, and we do 10 to the power of 4 divided by 20. Multiply that by 0.775, and you should come up with 1.23 volts. Now on a mixing console, you're also going to see VU meters, which are called volume unit meters, which are an average meter, not to be confused with peak meters. So they don't quite respond as quickly as peak meters, but on old analog consoles you will see VU quite often. And you'll also see something called 0 VU, which is pegged to a specific voltage. Now in pro audio, 0 VU is commonly plus 4 dBu. In broadcast consoles and some broadcast specific equipment, 0 VU is going to be plus 8. So if you're into radio or TV, you may possibly run into consoles and recorders and processing gear that will have a 0 VU value of plus 8 dBu. And in consumer audio, 0 VU is going to be minus 10 dB big V. So whenever you're looking at, okay, what is 0 VU or the nominal operating level on your meters, you have to be careful of what the reference value is. So you have some gear, some consumer gear that might be minus 10. Your 0 VU is obviously going to be much different than a 0 VU on a mixing console. Now again, on some mixing consoles or other gear, you're going to see this 0 VU value on some of your meters. Now in order to figure out what the heck that is, again, we have to figure out what industry it's designed for, if it's pro audio or broadcast or consumer. Of course, here's where reading the manual is, of course, most helpful. But you can, of course, make an educated guess. Like on most of our mixing consoles, 0 VU is going to be plus 4 dBu. So you see those things say plus 4 out or minus 10 out. Those are 0 VU outs for a specific type of target device. So if you're going to a consumer recorder like a DVD recorder or, heaven forbid, an old VCR, those are typically going to be minus 10 devices. So 0 VU is going to be minus 10 dB big V on those devices. This all sounds a little confusing, in which it tends to be, but it's important to know that when you're interfacing gear and you're trying to get consistent levels or the correct level between them, you always have to bring them to the same common denominator. Because if you have a VU meter on one device and a destination device, you have a dBu meter, you really need to know what the levels really are when you're going between those two so that you can optimize the levels. So while it is a bit confusing, it's definitely worth the time to decipher what is 0 VU and in terms of dBu and getting everything on the same page. So if you see 0 VU equals 1.23 volts, well, you can run it through the calculator and convert volts to dBu, and you'll see that 1.23 volts is plus 4 dBu. And so that's going to be the pro audio industry. 1.95 volts is also very common. Converting that to dBu, that's plus 8. So that's going to be the broadcast industry. And 0.316, well, we only have one left. Obviously, that's a lot lower. That's going to be our minus 10 dB big V value. And again, we can take that voltage into our dB big V conversion formula. 20 log of 0.316 divided by 1. Go through that logarithm calculation, and you'll come out with minus 10 dB big V. And so that's going to be our consumer industry. Now, if there wasn't enough confusion, dBFS will really make your head explode, because dB full scale, which is used in almost all digital devices, represents the maximum input recording level or maximum signal level that the device can handle. So it's another way of looking at it is, okay, a 16-bit or 32-bit recorder, whatever, how many bits it is, 0 dBFS is filling up all of those bits. So if you're going from an A to D converter, the maximum input voltage in an analog sense equals 0 dBFS. It's the most that it can handle without overloading. So it's kind of the Price is Right of recording levels. So if you watched the old game show Price is Right, in the bidding round they'd have to bid to the closest dollar possible without going over the value. Well, it's the same way here. You want to try and get as close to 0 dBFS as possible to maximize your signals, but if you go over, you end up getting some digital distortion, or you end up kicking in the fail-safe compressors or limiters, and it ends up affecting your sound that way. So it's one of those things where you want to try and get as close as possible without going over. So all of your values are typically going to be minus dBFS, with 0 dBFS being the maximum. Now, why does this make your head explode? Well, the problem is that every device is different when you're interfacing in an analog world. Just because 0 dBFS on one device is 0 dBFS does not mean that 0 dBFS is the same on another device. Now, they're only the same when you're connecting them digitally, but when you're connecting them via analog, if you're sending, say, the output of your mixing console through your analog outputs and sending them into two different digital recorders, they could have completely different dBFS values. I'll give you an example. Let's say digital recorder number 1, let's say an old DAT recorder. We'll have digital recorder number 2, which might be a CDR. Now the DAT recorder, let's say that one has a maximum input level of 20 volts. And the CDR has a maximum input level of 24 volts. Well, obviously if we send a signal out that's 20 volts, it's going to be 0 dBFS on the old DAT recorder. But the CDR that has a maximum input level of 24 volts, it's still going to have 4 volts of difference, so it's not going to be anywhere near 0 dBFS on that particular device. So when you throw analog into the mix, it makes these digital scales kind of arbitrary. So you really have to figure out, okay, what is the maximum analog input level in terms of dBu, and then that's going to be a comparison of dBFS. So if the maximum input level of that DAT recorder is, say, 18 dBu, then 18 dBu equals 0 dBFS for that device. But let's try a couple examples here. Let's see if we can break out our formulas and try some of these samples here. So we measure voltage of 3.5 volts. What is that in dBu? Well, let's get our calculator out here. And one of the most important parts is actually figuring out how your calculator works so that you plug values in the right order. And quite honestly, once you have the formulas in front of you, really this is the only difficult part, is making sure that your calculator works the way you want it to. So again, if we look at the formula for voltage to dBu, it's 20 times the logarithm of the value, which in this case is 3.5 volts, divided by the reference. Now the reference for dBu is 0.775 volts. So first, let's take 3.5 volts, divide that by 0.775 volts, because remember, again, it's our value divided by our reference, and our reference here is 0.775 volts. So we have this value, 4.5, and we want to take the log of that, and we'll multiply that by 20. So 3.5 volts translates to plus 13.1 dBu. Not too bad, right? So we'll clear that out. Let's try the next one. 0.65 volts. What's that in dB big V? Well, again, our reference value for dB big V is 1, so we basically take 0.65 divided by 1. Oh, no, that's 0.65, okay, so we take our logarithm of that, and then multiply that by 20. That gives us minus 3.74 dB big V. And again, if we do it in the right order, we will get the correct positive or negative value for that. So yeah, it's minus 3.7 dB big V. That's our conversion for 0.65 volts. Now let's do one of our dBSPL comparisons here. Now if we want to turn 42 dynes per centimeter squared into dBSPL. All right, let's clear this out and try it. So we take again, 42 divided by our reference, which as you might recall is 0.0002 dynes per centimeter squared. So that's 210,000. Take the logarithm of that, and again, because it's pressure, we multiply by 20, and our value is 106 dBSPL. So 42 dynes per centimeter squared is pretty loud. Now, what's 0 dBFS in terms of dBu or dB big V? Well, again, if you look at a spec sheet and say that, as we might recall, our DAT machine has a maximum input level of, say, 20 volts. So let's figure out what that is in dBu. So 20 volts divided by our reference in dBu, which is 0.775 volts. Gives us this value here. I'll take the logarithm of that. And again, we're talking about voltages. So we have our 20 multiplier. And for a device that has a maximum input voltage of 20 volts, the dBu value is plus 28 dBu. So for a given device, then 0 dBFS equals plus 28 dBu if its maximum input voltage is 20 volts. And again, these are all things that you're going to find on the spec sheets of the devices, or the user manual, or some other reference from the manufacturer itself. Now here's an interesting one as well, because remember, we've been talking a lot about dBu, dB big V, dBSPL, some of these more concrete values that we're tagging to dBs. But again, dB is simply a comparison. We've been comparing it to known references, but what if we have arbitrary references? Like, let's say we upgrade from a 100 watt amplifier to a 250 watt amplifier. What's the dB improvement there? Okay, so if we break down the formula here, again, we're talking about watts, so it's going to be a 10 times the log of value divided by the reference. So in this case, we're going from a 100 watt to a 250 watt amplifier. So our reference value in this case is going to be 100 watts. So let's take 250, because that's our value. We want to divide that by our reference in this case, which is 100. 2.5. Let's take the log of that. And again, multiply by 10 because we're talking about power or watts. So here, as you can see, 3.97 rounded up, it's 4 dB. It's plus 4 dB change. So you'll get 4 dB greater output from a 250 watt amplifier versus a 100 watt amplifier. It might not seem like a whole lot when you're over doubling the amount of watts. So let's do another example here. Let's say you go from a 5,000 watt amplifier to a 10,000 watt amplifier. That's an increase of 5,000 watts, right? It's going to be huge. So, well, let's see. Is it? So we're going to the 10,000 watt amplifier from our reference, which is 5,000. Gives us 2. And we're going to take the logarithm of that, times 10, giving us a whopping 3 dB increase for an increase of 5,000 watts when you're starting from a 5,000 watt amplifier and you're going to a 10,000 watt amplifier. One might think that because that's 5,000 more watts that you're going to get an enormous amount of increase. Well, again, it's all about ratios. In this case, it's still a 2-to-1 ratio. When you double the watts, you only get 3 dB increase. But if you double pressure, you get a 6 dB change. Or if you have the pressure, then you get 6 dB decrease. And with power, we just discovered you double or halve it, there's a 3 dB change, either 3 dB up or 3 dB down. So double it, you increase 3 dB. Cut it in half, you lose 3 dB. So if one of your classes is really expensive books and you have to sell your 200 watt amplifier and downgrade to a 100 watt amplifier, well, you're only going to lose about 3 dB of output, so could be worse, right? Now, subjective dBSPLs. It's important to know what we hear versus what we measure. So some changes that we might perceive as being a little bit louder or twice as loud or somewhat louder, noticeably louder, that's going to be different than the measured values. So here 1 dB is generally accepted as the smallest noticeable change, which is why 1.5 dB is a common volume step on TVs. And you ever notice whenever you change the volume on a TV, you never just click one time. You always tend to step it up 1 or 2 steps at least, at least 2 or 3 steps on the TV when you're changing the volume control. Well, that's because generally speaking, we only really notice a change of about 3 dB for make it a little bit louder. Now, we as audio engineers, of course, can notice things significantly less than 3 dB, of course, because we all have golden ears. But for the lay person out there, that's why you tend to see people changing volume in steps of 2 or 3 at a time, since that tends to make it more noticeable of a difference. And that's where we're going to pause for today. We'll let some of this information sink in, and we'll see you next time for another exciting audio electronics topic.